Now we are on the last topic of colligative properties of solutions, which is also the last topic of this chapter. There are four colligative properties: vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. The first three were covered in the last episode. Now we look at the last one, osmotic pressure. Osmotic pressure is related to a natural process that is called osmosis. So what is osmosis? Osmosis is the passage of a solvent through a semi-permeable membrane, separating a dilute solution or pure solvent from a more concentrated solution. Looking at this description, you may not know what is going on actually. But slow down, that's okay. We're going to look at it again later. Before that, let's clarify what is a semi-permeable membrane. It is a membrane that allows the passage of certain types of molecules, usually it's the solvent water, but prohibits the passage of other types of molecules. Basically, in the case that we're going to talk about here, it is a kind of membrane that only allows water passing through. It blocks all other particles. All right, let's look at this picture here to talk about the osmosis process. It starts from beaker A. In beaker A, we have a solution, dilute solution in the beaker, either dilute solution or a solvent. Inside the tube, we have more concentrated solution. At the end of the tube, it is covered by a semi-permeable membrane. Well, once you soak the tube into the dilute solution, if the surface level is at the same level at the beginning, now water, the solvent water, will pass through this membrane and flow back and forth. The picture is a little confusing because when you look at the picture, it looks like there's only a flow of water molecules into the tube. That is not correct. Water molecules flow both into and out of the tube. However, because the inside the beaker, because the solution in the beaker is more diluted, which means you have relatively more solvent particles than the ones in the tube. As a result, you see a net flow. You see a net flow of water solvent into the tube. As an observer of this experiment, what do you see? You see the surface of the inside liquid start to rise because you have net flow of water into it. At the same time, when water flows in, the inside solution in the tube becomes more and more diluted. Which also means, along with the time going on, the water flowing out from the inside tube to the beaker, the rate of the water flowing out of the tube is increasing. So now we move our eyes to beaker B. More and more water is flowing inside into the tube. The surface keeps rising. The inside solution becomes more and more diluted. Now you see, eventually at some time, the flow of the water into and out of the tube will be happening at an equal rate. At that moment, the surface of the liquid in the tube will stop rising. So the osmosis is actually a process. You will see a net flow of solvent from a diluted end to the more concentrated end of the solution. That is osmosis. Now, what is osmotic pressure then? Now let's use this setup again to talk about it. We'll set up the experiment as what we did on the last slide. We have a beaker outside, we have a dilute solution inside, we have a more concentrated solution separated by a semi-permeable membrane. The level of the surfaces inside and outside is at the same level. Now we know if we don't do anything, there will be a net flow of water into the tube, and the surface of the liquid inside the tube will rise. Well, let's do this. Let's cover the surface of the liquid inside the tube and apply a pressure on it. We push it. Once you apply a pressure on it, you're pushing the water molecule flowing out of the tube. You are making that one happening faster. Does that make sense to you? You push it, water will be flowing out of the tube to the beaker faster than before. If the pressure is high enough at some point so that the water will be flowing out of the tube at an equal rate as the water flowing into the tube, when pressure is at that level, then you are not going to see any net flow of solvent back and forth. The surface of the inside the tube will stay there forever. So basically, that pressure required is called osmotic pressure. So basically, osmotic pressure is the pressure required to stop the osmosis from happening for a solution. The pressure must be applied to prevent the net flow of solvent through a semi-permeable membrane from a solution of lower concentration to a solution of higher concentration. Basically, the pressure required to prevent the osmosis from happening. Needless to say, depending on the concentration, the number of particles in the tube, the more concentrated it is, the higher pressure will be required. So osmotic pressure is related to the number of particles inside a solution. The more particles you have, the higher the osmotic pressure. Since we are on the osmotic pressure topic, we are going to introduce an osmolarity, or osmo. Osmolarity is used to compare the osmotic pressures and other colligative properties of a solution, be it vapor pressure, boiling point, freezing point of a solution. We can compare the colligative properties of solutions by using osmolarity. What is that? Osmolarity equals molarity, the concentration of the solute, times by I. We kind of did this earlier, but we didn't mention osmolarity before. We did this actually in the last episode. So what is I? I is the number of particles produced from the dissociation of one formula unit of the solute. If you still don't quite sure what it is talking about, let's use an example here. Let's do the exercise here. What is the osmolarity of a 3M NaCl solution, sodium chloride? Well, we know the molarity, 3M. However, the molarity is the concentration of the solute, not the number of particles. Each NaCl, when it is dissolved in water, it produces two particles, one sodium ion, 1 chloride ion. As a result, I equals 2 for NaCl. So osmolarity of the solution equals molarity multiplied by 2 in this case, which is 6 osmol. So what do we need this for? You can use osmolarity to compare which solution had a higher or lower vapor pressure, boiling point, freezing point, and osmotic pressure. Here is the conclusion. The higher the osmolarity, the stronger the colligative properties, which means the lower the vapor pressure, the higher the boiling point, the lower the freezing point, and the higher the osmotic pressure. All right, that's it for this episode.